Hello everyone, today we are going to discuss CodeChef long challenge problem REBIT. First of all, we will discuss problem statement. Then we will discuss how to evaluate XOR, OR and AND expressions. We will understand a little bit tree data structure. We will also learn how to convert Infix to Postfix, and last, how to evaluate Postfix expression. So let's start with the problem statement. According to problem statement, we are given a string in the form of hash and operators. Hash here refers to operand and operators are in the form of AND, OR, XOR, AND, OR, XOR. And operand is in the form of hash, which represents four things: 0, 1, small a and capital A. 0 and 1 are clear. Small a refers to 0 or 1 and correspondingly capital A refers to 1 minus a. That is, if small a is 0, capital A is 1, and small a is 1, then capital A is 0. Now, given an expression such that in the form of suppose this, we need to find the probability what it evaluates to. For example, it may evaluate to 0, 1, small a, capital A, depending on the value of these two hashes. For example, if these two hashes are 0 and 0, then the AND evaluates to 0. If these are 1, 1, then AND evaluates to 1. If these are A, AND evaluates to A, capital A, AND evaluates to capital A, and further more possibilities. There are 4 possible values of this hash and 4 possible values of this hash. So, total possibilities are 4 to the power 2. Total possibilities that our expression may evaluate to are 4 to the power n, where n refers to number of hashes. This is the problem statement and we have to find the probability of each value. Because probabilities can be in the form of fraction, obviously these are in the form of fraction. For example, the initial value of hash is where we have to select 0, 1, a and capital A. The probability of selecting them are equal. So these are 1 by 4, 1 by 4, 1 by 4. These are in the form of fraction. So to convert this fraction into a number, we need to represent our fraction. We need to mod our fraction with the number which is provided in question, which is 998244353, which is a prime number. Selecting a number m, selecting a number m such that like this, why we select a prime number? Prime number is selected so that there are minimum collisions, so that some fractions are like this, a over b, and when we mod it by m, a prime number, a non-prime number, they may evaluate to a number, say x, and another fraction may also evaluate to the number x. This leads to collision. To minimize collision, we choose a prime number so that there are minimum number of common factors. Common factors come. This is our problem statement. Now let's move to the second part. Understanding XOR, OR and AND expression. AND, OR and XOR requires two operands. AB, because they are binary. Binary operators require two operands. So we can map this situation to a BST. Where every node, such as an operator, has two children, A and B, and together they will evaluate to a value. But here in our question, we have four possibilities. That is 0, 1, small a and capital A. For understanding, we can think of capital A and small a as having symmetrical situations. Because A is A bar, similar to A bar. For clear understanding, let's construct a table. As we have four options and we are going to evaluate a binary operator, say any operator, and we have four options, two hashes, then total possibilities are 4 square, that is 16. So let's pick up every match. Let this be A, B, 0, 0, 0, 1. These are all possibilities of A with B, of 0 with B, 1 with B, small a and capital A. We have to evaluate AND, OR and XOR. We note that for 0, 0, AND is 0, OR is 0, XOR is 0. Similarly, 0, 1, AND is 0, 1 and XOR is 1. For A0, whether A is 0 or 1, its AND with 1 is 0 will give 0, 0, 0 or will give 0, 0, 1 or will give 1. So this is A. 0, 0 will give 0, 0, 1 will give 1. So this is A. Similar wise we can fill the whole table. Let me show you quickly. Here I have constructed the table. Clearly in case of AND, we can see we have 4 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 zeros. So for AND we can say for 0 we have 9 by 16 chances. For 1 we have 1 by 16 chance. For small a we have 1, 2, 3, 3 by 16 chance, and for capital A we have 1, 2, 3, 3 by 16 chance. These both are symmetrical. And their sum 9, 10, 11, 12, 13, 14, 15, 16 evaluates to 1. So it is proper. Now let's move to OR and XOR. Similarly, counting for OR, we will get 1 by 16 for 0, 9 by 16 for 1, 3 by 16 and 3 by 16 for small and capital A. And for OR, we will get 4 by 16, 4 by 16, 4 by 16 and 4 by 16. These are our chances of evaluating to each possibility. 0, 1, small and capital A for each operator. So we have completed a bit about XOR, OR and AND expressions. Now we will understand a little about tree, that is BST. Given an expression like this, we know that we need to evaluate AND over two of our operands. And if we are given an expression like this, then we know for these two hashes, for these two we need to do AND, and for these two we need to do OR, and whatever be the result of these two, we need to XOR it. It looks like a BST. Very simple BST. One more expression if we take, like this. First we took hash, and first the expression will be evaluated. First the brackets, first the expression inside bracket will be evaluated. So we will get hash, hash, and we have done hash, hash and its AND. The result of this will be evaluated with this hash over here and XOR. It is a BST. Simple mapping to a BST. Now we know that given an expression like this, how to evaluate it with the help of this. For example, we know the probability of getting 0, 1a and capital A when we have an expression like this. We found it earlier to be 9 by 16, 1 by 16 and 3 by 16 and 3 by 16. For this, we can evaluate up to this point easily. We have found this to be 9 by 16, 1 by 16, 3 by 16, 3 by 16. And for this we found it to be 1 by 16, 9 by 16, 3 by 16, 3 by 16. From this we need to evaluate this. If we took it to be like this, that 9 by 16 of and this is for 0, 1 by 16, 1, A, capital A, for and for or, now we need to look into our table to evaluate this XOR. We need to look into a table. First we need to find the final probability of getting 0, 1, small a and capital A. For 0, let's look into the table. 0 we can get with A, B, 0, with A, B, 1, 1, with A, and with capital A, and with sorry, I missed something. It is not this, and this 0. So we can get in XOR 0 value equal to this. A of, say A has 4 values, B also has 4 values, A, after this part is A, and after this part is B for this, for XOR. So A has 4 values, B has 4 values corresponding to 0, 1, small a and capital A, 0, 1, small a and capital A. We know that the XOR value of 0 will be obtained from 0, 0, 1, 1, A and capital A, 0, 0, 1, 1, A, capital A and capital A. So our value will be 9 by 16 to 1 by 16 plus 1 by 16 to 9 by 16 plus 3 by 16 into 3 by 16 plus 3 by 16 into 3 by 16. A has 4 values, B has 4 values, we have found all their combination values here, and we are using this table to find the value of XOR, XOR of A and B. What is the probability that it evaluates to 0? And it will evaluate to 0 only using A0, B0, A1, B1, A small a, B small a capital A, B capital A. Similarly for 1, this is for 0, 1. For 1, when the XOR value will evaluate to 1. Let's look into the table. XOR is 1 when A and B are 0, 1. This value, this value, this value, and this value. So we will take A's 0th value into probability of A's 0 value into probability of B's 1 value plus probability of B's 0 and probability of A's 1 plus probability of A is A and B is capital A, and probability of A is capital A and probability of B is small a. In this way we will get the value of 1. Similarly, we will see the value of small a and capital A when they will evaluate to small a and capital A using the table. We will multiply their corresponding probabilities and sum them up to get these values. In this way, we will proceed in bottom-up manner, bottom to up to reach this node. We use probabilities here and here. We use 1 by 4 to evaluate this, and these two will be further used to evaluate this XOR. How we used 1 by 4 to evaluate this expression is as from the table. We found the probability. Using these probability, we can make all possible combinations, or we can use the table and generalize it to derive this value. Similarly, we can use 1 by 4 for all and 1 by 4 for all to derive this as we did earlier, and 1 by 4 this with this. It will act as A, and the expression we evaluate with this will act as B, and this will be used to derive probability of this. We have completed this. Now we will move to Infix To Post Fix. First of all, why Infix To Post Fix? We will be given a string like this. Given a string, we know how to find the probability given we have constructed the tree. if we know the order how to proceed, we first calculate this result and use this result to evaluate this. But how to construct this tree? That is how to know how to evaluate. For this we need to convert infix expression given to us to postfix. Once the expression is converted into postfix, we need to evaluate that expression and simultaneously know the probability. How to convert an infix expression to postfix? Once we convert an expression to postfix, for example this expression into postfix, it will look like this. It is basically the post order traversal of the tree. Post order traversal will look like this. For example, we will first get hash and then we'll get hash and or, and then this. Advantage of converting into postfix is that we do not need to keep track of the braces. We don't need to keep track of precedence. Once we construct a postfix expression, we can evaluate it by using valuation of postfix. The method to convert an infix to postfix. First of all, whatever the string is, say we are given a string like this, we need to first put closing parenthesis in the end and construct a stack. In the stack, first we input a closing brace. Then we will start evaluating from the left end. Here we encounter a left parenthesis, so we push it onto the stack. And now we move further. Now we encounter an operand. P is our resultant postfix string. This postfix string. When we encounter an operand, add it to P. When we encounter an operator, we have to pop all the operators which have precedence equal to this operator or less than it. But here in the question we are given a string like this, that we do not need to keep track of precedence. Only braces have the highest precedence, then all our operators will be guarded by parentheses. So we need not to take care of parentheses. Whenever we encounter operator, we need to push all the operators, because here all the operators we took as same precedence. We need to push all the operators out of the stack and push this operator inside the stack. So we have to push the operators up till the first opening parenthesis. As we have no operator, we just push and into the stack. Then we move forward and we got an hash. We append it into the string. We move forward we encountered a closing parenthesis. When we encounter a closing parenthesis, we push all the elements of the stack. We pop all the elements from the stack until we encounter a closing and opening parenthesis. So we push and out of the stack and add it to Q. So we pop and out of the stack and add it to P, and simultaneously remove this also. This indicates that the first closing and opening parentheses have matched and we have evaluated up to this. Now we encounter an operator OR, and there is no operator in the stack, so we push it into the stack. We move forward and we got an opening parenthesis. We push it into the stack, move forward, and now we got a hash, so we append it into the string. We got an operator. Let's make this little bit clear here. We have this in a stack, we have this, and now we are to this. So we push it into a stack and move forward. We got this and we append it into a string. Now we got a closing parenthesis. We pop it out of the stack, and this also. Add the operator to P. Now we move forward. We encountered closing braces again, so we push this operator out of the stack, append it into the string, and simultaneously push this part also. Pop this part also from the stack. This is our resultant postfix expression. Let's do it a bit more quickly. First we add this to stack, and closing parenthesis is appended to the string. We encountered opening parenthesis, we put it on the stack. We encountered hash, we append it to the string. We encountered another operator, we add it to stack. We encountered hash, we appended it into string. We encountered closing parenthesis. We pop all the operators till the first opening parenthesis we encountered into the stack. We pop this, add it to Q, and we encountered opening parenthesis here, so we just pop it. Now we move to everything over here. We add OR into the stack. We add closing parenthesis into the stack. We add hash to the string. We hash and we append hash into the stack. We append hash to the string. We encounter closing parenthesis, so we pop and append it to string. We pop the closing parenthesis out of the stack, and now we encountered closing parenthesis. So this is the value in our stack. We pop it from the stack and append it to the string. Later, now we pop it from the stack, and this is our postfix expression. Now we have obtained a postfix expression. Now postfix to evaluation. How to evaluate the postfix expression. Now we will learn this. For this we need stack. Our string was this is stack. First, to evaluate postfix expression, we first add a sentinel to the end of the string to indicate the end of the string. Now, until the sentinel is encountered, we start from the left of the string and move forward one by one. If an operand is encountered, we push it to the stack. So another operand, we push it to the stack. When an operator is encountered, as this is a binary operator, we push two elements from the stack. That is, say this is #1, this is #2. We calculate #1, operator #2, and whatever is the result, we push it into the stack again. So the stack will look like, which is #1 and #2, #1 or #2, which was the expression first we need to evaluate. This is postfix, but its corresponding infix was yet. This part is obtained here. Now we move further, add hash, add another hash, this one, and now we obtained and. So we popped the top two elements, hash, and its result is pushed back into the stack. So we got result 1, which was already there, and result 2, which is same as this. Now we encountered an operand again, or. So we pop the top two elements from the stack and evaluate or, say R1, R2, R1, so R2, and push it into the stack. Final result. This result is hash and hash. Then we sort it, or then hash, sort hash. We evaluated the expression. We evaluate the expression by converted first into postfix, then evaluating the postfix, we saw that we are evaluating the same infix expression. So we saw Infix To Post Fix, how to evaluate postfix. Problem statement is clear. We have constructed table for XOR, OR, and AND expressions, operators, and we studied a little bit about tree data structure, as here. Infix To Post Fix and how to evaluate the expression, postfix expression. Now we will look at the flow of code. First we will start with taking input. First we will input the string. This string for evaluation need to be converted to postfix. This string is infix. We convert it into postfix for evaluation, to get rid of brackets, to get rid of precedence. From postfix we start evaluating postfix expression. The part where we had two operands A and B in the stack, for example the tree was like this, say hash. If the tree is like this, say here these are A and B and we evaluated the AND, its postfix will look like hash, and hash OR. So first we will convert it into this, convert the given string into this, and then when we evaluate it, say this is A, this is B, and we evaluated and we got AND. We pop this and this out of the stack. We calculated A and B. That is, we reached this part. When we calculated A and B, here we will call our function AB operator, which will calculate probability. And when this probability is calculated, say in the form of array for 0, 1, A, capital A, which this function will return, we will pop this result into our stack. This result will be pushed into the stack, and then we further evaluate this. So this array is present over here. We add hash. This hash itself is an array of 1 by 4, 1 by 4, 1 by 4, 1 by 4, and then we encountered OR this array or this array, hash, this hash, and this one over here. We evaluate another array calling the function A, B, and our operator. This will be returned and pushed into the stack, while these two will be popped, and the result in stack is our answer. Now, since we know the denominator will always be 4 to the power n, where n are the number of hashes, we have to calculate only numerator. So for the initial hash, we can take the probability 1, 1, 1, 1, since we know the denominator always. We know this is all 1 by 4, but we can write on the numerator here. We know that if in a string such as like this, if there are 3 hashes, total possibilities are this. So initially when we got a string like this, we got hash, so we push this array 1 1 1 1 into the stack, we got its postfix will look like this. So we got another hash, then we got and, we'll evaluate the and, the resultant array we get, we push it into the stack resultant, and then we push hash to the stack again 1111 and validate OR of 1111 with the result. And this is our answer. Now we will look at the code for this.